Hello, and welcome back to another episode with It's Dr. Dan. And today we're going to be learning how to count valence electrons and draw Lewis structures for atoms, cations, and anions. So we're not going to be looking at the bonding picture, but just how do you do the basics, right? How to stick to your fundamentals. So let's just get into it. So the first thing is, let's say if I have nitrogen, which if you kind of remember from your chemistry class, well, that has an atomic number of 7. So if you kind of remember, well, what is an atom? Atoms are inherently neutral, meaning they have the same number of protons as they do electrons. So for something like nitrogen, well, if it has 7 protons, being that we have our number here, then it also has 7 electrons. And when you were starting that off, when you first learned about electrons, typically we learn how to organize it via the Bohr model, which if you remember, well, that first level, that shell, it will have 2 electrons. And then the next shell is going to have the other 5 electrons evenly spread out. So we have 1, 2, 3, 4, and 5 all spread out. Now, what do all of these represent? Well, we have our different levels. Well, the ones that we are interested in today are the outermost level. These are referred to as the valence electrons. So it's your outer shell. So one way to look at this atom is it's like layers of an onion, right? You can peel off those individual layers. Well, what layer do you peel first? Well, it's the outermost. So when it comes to cations and anions, well, that's what's going to be behaving in all of this chemistry, are those outer levels. Now, you might also have to label what the inner levels are. These are referred to as the core electrons, which are so close to the nucleus, right, the center of the atom, that typically they don't behave in that many chemical reactions. So the valence level is what we're going to look at. So we're going to learn some methods on how to count them, some simple ones, so that we just using your periodic table, what you are given on an exam or on a homework for most of your chemistry classes. And then we'll go through different ways to draw Lewis dot structures. Let's get at some different examples. Now, the easiest method for being able to count valence electrons is by using your periodic table and marking the columns found on the periodic table. So if we look at this and we look at the first column, what we're going to do is we're going to just label it like how you would number any column that you would see, which would be with the number 1. So when we do that, we label the first one as number 1, the second column with number 2. And what those represent is the number of valence electrons for all of the elements in that particular group or family, or also column. So for example, hydrogen, lithium, and sodium, they all have 1 valence electron in their outermost layer, right? So if you're kind of just to show those as quick examples, right? If you think of hydrogen, well, it has an electron configuration of 1s1, meaning that it has 1 electron in its outermost level, which is 1. If you think of lithium, well, that one is 1s2, and then 2s1. Notice once again, we have 1 electron in each of those levels. And then if we go down to sodium, and I do the same thing where I write down its electron configuration, well, notice we have the same trend where we have 1 electron in its outermost layer, which is that highest number, right? So 1, 2, 3, those are the highest numbers. So the second column, right, where beryllium and magnesium are, we can also put helium in that position as well. So helium, even though it is a noble gas and is on the far right-hand side of the periodic table, we can pretend that helium is located here for valence electron purposes, being that helium also has 2 electrons. So then as we kind of go through that periodic table, right, we can fill in the rest of the columns. We can pretty much kind of move this for now, or we can say like, okay, let's kind of get rid of helium for at the moment where it's going to be on that far side, gone away, right? And we're going to put, okay, so now that we have those different numbers, these represent the number of valence electrons in their outermost layer. let's practice drawing these as Lewis structures for many of these examples that we have listed above. All right, so our first example of going through how to draw different Lewis dot structures for atoms. So let's just go through our periodic table, practicing counting valence electrons. So if we start with the first one, which is hydrogen, right? Hydrogen's all the way up here on that top left side of the periodic table. So, and that belongs in the s orbital, right? So that's its highest level. So I wrote down all the electron configurations for these elements for us because we just want to focus on how to write the notation. So if I have hydrogen, right, 1s1, we can see that, well, that is its outermost level, is this 1s1 area. Now, same thing with helium, right? 1s2, that is its highest level. So what we're going to do is we're going to draw the atom first of hydrogen, and we're going to use a dot to represent its valence electron. So being that this one has one single valence electron, we'll just write that as H with a dot. And it doesn't matter exactly where you put that dot. You can put it on the top, you can put it on the left, you can put it on the bottom. They all represent that we have one valence electron around our hydrogen. And this is going to be important for when you get into covalent bonding, all about how we can make bonds to share electrons, which will help you be able to illustrate that, which there are other videos on my channel as well to help go into covalent bonding. Now with helium, helium is the same idea. So what we're going to be doing this time as well, we have a complete orbital for helium, meaning we have 2 electrons. It has a complete level, right? Remember this, even though I wrote it in the little dashed lines up here, this is like a noble gas, right? Meaning that it is happy. It's fulfilling what we refer to as, for this one, is the duet rule, right? It has a complete level. So for this one, it's going to be a little different than all the others. We're going to put those 2 dots together to help represent that this has a complete orbital. And we can put them like I did before, is on any side, as long as you have some kind of consistency with the way you write these. Now, so that's hydrogen, helium, right? We have 2 valence electrons, 2 dots. So we have 1 valence electron, right? 2 valence electrons, and that's going off the columns of our periodic table. So 1 and 2. And just to kind of help illustrate that, right? 1 and 2 here. So our next one, right, is going to be boron and aluminum. So if I have, sorry, all right, I go to the next one. So if I go down to lithium, right, lithium and beryllium. So lithium is right below hydrogen. So how many valence electrons should it have? Well, based on our trend here, it should also have 1. But I thought, but lithium has 3 electrons. How is that the case? Well, what we're going to be doing is counting its highest level. So when you are looking at your periodic table, right, we can see that lithium is right here, right? It falls under column number 1. So what we can do is by seeing that, we know it has 1 valence electron, whether we have the electron configuration or not. But one thing to keep in mind is, well, being that we do, the electron configuration, all we are doing is counting S and P electrons in the highest level. That is it. So we only count S and P. All right, so I'm going to write that down here because it's really important to see. Only count S and P, and that has to be the highest, okay? So keep that in mind. So that's all we're going to be counting. So with lithium, right, what we can see, the highest one is 2s1. So once again, we have that 1 feature here as our answer. So 1 valence electron, and it is going to also be just 1 single dot. So let's do this one in a different color. So lithium has just 1 dot, and as before, it doesn't matter where you put it. Let's go on to the next. Well, the next one, beryllium, right? Once again, we can see our highest level is 2s2. How many do we have here? Well, now we have 2 valence electrons in that highest orbital. So now we can do is write, well, 2 dots this time. So we do beryllium, and we write 1, 2, and notice the difference between beryllium and helium, right? Helium has a complete level. So we write them together. However, beryllium does not. It still has room to grow. And that's because we now have access to the p electrons. So when you go down to boron, notice how in the second level, we have p electrons. So we don't have 2 anymore, but we have 3 valence electrons because we're moving down our periodic table, right? 1, 2, 3. So boron now has those 3. So, and as we keep growing, we can kind of make some predictions here, right? Is that, well, when we go to carbon, well, that's going to be 4 valence electrons. And we can show this, right? The whole idea is that as we grow, we're going to keep putting dots on every side. So with boron, we'll do 1, 2, 3. With carbon, we'll do 1, 2, 3, 4. And the way we're drawing these is imagine that our element is in a little box that we're filling the dots around each side, okay? Now, what happens when we go over 4? Well, if we go to nitrogen, which is now 5 valence electrons, and the way to kind of highlight that, just to keep that highlighting up, right? So boron was these 2, carbon was these 2 here, oops. And then nitrogen was these 5, right? So we're adding up the superscripts. So for nitrogen, 2 plus 3 is 5. So when we are doing this, we are going to write our nitrogen, and then we are going to put a dot on each side, right? 1, 2, 3, 4. And then we're going to double up our dots on another side. It does not matter where the double up is happening. Personally, I prefer the top. That's what most people do when they are drawing this, right? So you can either draw it like that, or if you want to, you can write dot, 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 and maybe you have them both on the right-hand side. There is no particular method as long as you are being consistent. You will hear some different professors, they'll tell you like, oh, it has to be top, down, left, right. It does not matter. With oxygen, all right, same idea here, right? We're going to go down that. We're going to highlight our valence electrons. So 2 plus 4, which means 6 valence electrons. Notice how that's also matching up with our column, right? So oxygen's here in the 6th one. You see fluorine is 7, neon is 8. So we can keep building this. So why don't we do that? So we'll see that, okay, oxygen is 6, fluorine is 7, and then 8. And then we can write all of those little pieces for ourselves. So oxygen, we will do 1, 2, 3, 4, 5, 6. Fluorine will do 1, 2, 3, 4, 5, 6, 7. And then neon, which is our last one, we will do 1, 2, 3, 4, 5, 6, 7, and 8, right? So we're filling in all those sides all around our species. And this is how we do Lewis dot structures for just a normal atom. And remember, the goal for all these different elements is to get towards our noble gases, right? So either we want to achieve the octet rule, or we want to achieve the duet rule for hydrogen, helium, lithium, beryllium, around that area. We want to be a noble gas. So let's look at how to do this for cations and anions and look at the difference. All right, so our last example is talking all about cations and anions. And if you remember from my previous videos talking about ionic species, that was when we were gaining and losing electrons. So to remember that, losing an electron was all about being a cation. So meaning when you lose an electron, you are more positive. So cations are positive. So if you remember a cat, right, has paws, it is positive. So an anion is negative. Think of that negative thing where onions make you cry. That'll help you remember that onions are more negative, meaning more electrons, right? It's all about a balance of charges. So how do we do this when it comes to Lewis dot structures? Let's do a simple one. Let's say if I have hydrogen. Hydrogen has 1 dot, meaning that it has 1 s1. Well, hydrogen, what is the predictable charge of hydrogen? Well, being it's in that first column, it has a predictable charge of +1, right? So everything in that column would be a +1, this +2. Why don't we just fill in the rest of our charges as well? So let's say if I'll do -1, -2, -3 for our predictable charges. So hydrogen, it is prone to giving up an electron. So where is that going to come from? Well, it's going to come from our valence level, our outermost shell. So when that happens, well, let's say if we have H and it loses its electron, we will put that in brackets to denote that it lost its electron, and then we'll put a positive symbol. Notice how it doesn't have a dot anymore. It lost its electron. Now, let's try a different one. What if instead I do, we'll do oxygen, for example. So if I have oxygen, well, oxygen has how many dots? Well, if we go to our periodic table, we can double check that for ourselves. We can see that oxygen is at 6, so it should have 6 dots all around it. So when we go about and try to write that for ourselves, we're going to fill in all those little dots. So we have 1, 2, 3, 4, 5, 6, right? So it has 6 valence electrons. Now, if we want to draw, let's say, O2 minus, right? Well, what is the difference? Well, O2 minus means that it gained 2 electrons. So it has more electrons. This is an anion versus H plus, which was a cation. So when we are an anion, what we now need to do is not only do we want to show the 6 dots we had before, but we are going to be adding 2 dots as well. So we'll represent that in orange. Now, when we have those extra 2 dots, notice how the octet rule is satisfied, right? We have all 8 of them, and we can put here that 2 negative to tell you, hey, this is an ion that has extra electrons that are here. And this is going to be really important when you have to do ionic bonding, Lewis structures, and potentially covalent as well. It'll help guide you in seeing how many bonds these can do. Let's try another. So let's say if I had sodium. Sodium has 1 valence electron. Now, if I want to do sodium plus, well, how would I do that? Well, it would be just like so. You'd put it in brackets and put a plus sign. Now, depending on where you are learning chemistry, you can potentially show that what is its new valence level. Well, let's write it out. So sodium neutral has 1s2, 2s2, 2p6, 3s1, right? And we're going to be removing this outermost level. So sodium plus, on the other hand, well, it just has the same configuration as neon, right? So when I take this, it has the following configuration. So can you write it where we have 8 valence electrons? Well, you can. You can show that, okay, this has 8 valence electrons all around it, as long as you illustrate that it has a positive around it to tell you, hey, this is missing 1 electron. It has its complete octet. So you can show either or. Most of the time, though, this is the preferred and more common method. However, every class is a little bit different, which have different purposes. So keep that in mind. If you're not sure, you can always ask your professor or your teacher which one they prefer. But I know with my students, typically I'm more in favor of this one, but I know every class is a little different. So keep that in mind, right? A little warning. Anything you see on YouTube, you want to make sure you double check with your professor. So that is another example of a cation. Let's do one more. So what if I have, let's say, nitrogen? Well, nitrogen, let's check how many valence electrons this has. We can go to our periodic table. We can see that it is on column number 5 here. So it is right here where we see N is 7. That tells you 7 protons, 7 electrons, 5 of which are valence. So let's kind of talk about that for a second. So we have 7 total electrons. 5 are valence electrons. What about the other 2? What are they? Well, that means that there are 4 electrons, right? So all these added together is going to be making your total number of electrons. So keep that in mind, that all the core and valence added together equals your total electrons. So sometimes you might have a class that requires you to really to show both those sides. So now that we have our nitrogen here, we're going to write our dots. So we had 5, right? 1, 2, 3, 4, 5. Now let's try the anion form, right? If I tell you N3 minus, well, how is that going to be changing things? Well, being that this is 1s2, 2s2, 2p3. The N3 minus is going to be 1s2, 2s2, and this is going to be 2p6 as our change, right? So notice that that number goes up 3 because we are an anion. So when we draw our Lewis dot structure, we'll write 1, 2, 3, 4, 5, and then we'll put our three new dots as a to show that this is an anion, and then we would write in brackets with a 3 minus. This is how you can write Lewis dot structures for atoms, cations, and anions. I didn't see a lot of videos like this on YouTube, and I thought, let's just go over the basics. If you would like to go over covalent and molecular bonded bonds, go to my follow-up video on this, on how to draw Lewis structures. It's a little bit of an older video for now, but hopefully that can help you be able to understand these little basics. This is Dr. Dan, and I hope to see you all in the future, and I hope this helps. Thank you all for liking and subscribing, and I hope to see you all in the future. Bye now.